Okay, we go now to chapter 8, no? Dynamo voltage characteristic and external characteristic of generators. So when a generator is operated, it has an external characteristic. No? Depende sa klase ng generator na gagamitin mo. Yung external characteristic class, ito yung graph na nagpapakita ng pagbabago ng mga generator habang gumagana siya. Tawag doon external characteristic. So, pag may external characteristic, syempre, meron tayong tinatawag na voltage regulation. Ano ba ang kaugnayan ng voltage regulation sa external characteristic? Yung voltage regulation, ito yung pagbabago ng voltahe ng generator mula sa kawalan niya ng load hanggang sa pagkakaroon niya ng full load. Katulad nung nakikita ninyong formula, no? Itong formulang to. So, meron tayong tinatawag na flat compounded. Yung flat compounded na tinatawag natin, yan yung voltahe ng generator na walang load. Equal yun sa full load voltage. Kapag walang load, yung tinatawag mong flat compounded kapag yung no load voltage ay equal sa full load voltage. So sa kaso nito, equal siya sa zero. So where we have the following, no? Dito, voltage regulation, ang formula niya is voltage no load minus voltage full load divided by voltage full load times 100%. P sub R stands for percent voltage regulation, no? PNL, no load voltage. And yung tinatawag na voltage full load. Full load voltage yung tawag dito. So usually percent lagi ang unit niya, no? So we have the fundamental equation of generated voltage, no? Okay, fundamental equation of generated voltage. Ito yung naunang lecture natin, no, sa chapter 4, which is ganito, no? E is equal to the number of inductors times the flux times the number of poles times their speed divided by 60 times the number of parallel paths. Kung naka-Maxwell siya, kung naka-Maxwell itong magnetic flux, i-multiply mo sa times 10 to the negative 8. So, let A sub 1 of constant 1 is equal to the number of inductors times the number of poles divided by 60. Yung multiplying factor na 60 times the number of parallel paths. Yan. Equation to yan. No? So, itong number of inductors, itong number of poles, yung multiplying factor na 60 or conversion factor, itong parallel paths, number of parallel paths, lahat daw yan ay constant. Bakit naging constant? Kasi you can only change them by remodeling the machine. So, i-remodel mo lang yung machine para mabago mo siya. No? Pag-design ka ng panibago. Kasi mga constant na yan, mga hindi mo pwedeng baguhin. So, mababago mo lang siya kapag ni-remodel mo yung machine. Except yung 60, no? Kasi multiplying factor to eh. Wala kang magagawa rin dyan. Kaya constant yan. So, yung number of inductors, number of poles, yung multiplier na, yung conversion factor na 60 at yung number of parallel paths are constant. You can only change them by remodeling the machine. So, kinakailangan i-redesign mo uli yung machine at buuin mo uli, no, sa manufacturer para mabago mo yan. Isa-isahin natin, no, para maging malinaw. Yung say, yun yung number of inductors, ito. Ba't di mo mababago yung number of inductors? Nasa loob ng computation niya na yun ang number of terms na kailangan sa kanya. Ang isang term kasi ay binubuo ng dalawang inductors. Napakaraming inductors yan. So, hindi mo mababago yan na hindi mo pwede baguhin yan. I-remodel mo. Yung number of poles. Pag AC, pwede mo baguhin yung number of poles. It's a matter of computation lang with regards to the field, no? Nababago-bago mo kasi nagwa-wind ka ng poles sa field. Dun mismo sa pinaka-stator niya. Pag DC ang machine mo, yung magnet pole siya nakausli na parang ganito. No? Kung ito yung DC machine mo, may yung magnet poles nakausli ng ganyan. Yan ang isang mapapansin mo sa DC machine. Pag nagbukas ka ng motor or generator at nakita mong nakausli yung mga magnet poles, ibig sabihin DC machine yun. Naka-fix ang magnet poles ng DC machine. Hindi katulad sa AC, pwede mo siyang bago-baguhin, no? Pwede mo gawin 2 poles, 4 poles, 6 poles. Depende sa design na gusto mo. At depende rin sa bilis na kailangan mo. So, base dito sa formulang ito, no? I-substitute natin itong 2 sa 1. Paano mo maisa-substitute yan, no? So, ito yung say, ito yung 60, ito yung number of parallel paths, ito yung number of poles. So, ay gagawin mong K1. So, syempre, kung 2 substitute to 1, you have 2 in 1. So, you have the generated voltage E is equal to, tinawag natin constant, lahat yung binilugan ko kanina. Tapos, ang natira lang, itong magnetic flux na P, tsaka yung speed. Kaya KPN yung tawag dyan. Tawagin natin ngayon yan na equation 3. So, meron tayong formula ng inductor, no? Kasi, yung formula ng flux kasi ganito, no? Yung magnetic flux, may formula kasi ang magnetic flux na ganito. The number of inductor times the field current divided by the number of turns. Yan yung formula ng magnetic flux. Pero ang kailangan natin, formula ng inductor, i-derive natin. So let us solve for inductor. No? So if you solve for the inductor, you're going to have the number of turns times the number of flux divided by the number of field current. So therefore, simplify further, pwede mo siyang isulat na, or you can solve for the magnetic flux, no? Divided by the total number of turns. Tawagin natin yung number of turns at saka yung inductor na field constant. Ito, KF, which means field constant. Kaya pwede natin siyang isulat sa formula na to na therefore, we can write the formula of the magnetic flux as the field constant times the field current. Yan ngayon ang pwede natin tawagin na equation number 4. Substitute equation 4 in equation 3. So equation 4 in 3. So therefore, we can write E constant 1 multiplied by, lagay mo substitute mo dito sa magnetic flux. The magnetic flux has a formula of field constant times the field current. Kaya lagay ko ito na KF IF multiplied by the speed. Kasi may speed na given, no? Where the constant K can be called as K1, KF, or the constant, or the machine constant times the field constant, no? So therefore, we can write E is equal to KIF times the speed. Sa mga succeeding problems natin sa motors, magagamit natin itong mga formula ito. So, factors that affect the terminal voltage or voltage drop in a generator. Una, yung armature resistance drop, no? Yung resistance dun sa armature. May formula siya na armature current times the armature resistance. No, armature current times the armature resistance, where IA stands for armature current. and RA, armature resistance. Sumunod, isa pa sa mga nakakaapekto yung brush contact drop. Yung contact ng brush dun sa armature, sa commutator. Yung drop na yun o yung voltage drop na yun ay dahil sa electrical resistance sa pagitan ng brush at saka ng commutator. Ito yung kadalasang nagiging dahilan, kino-consider na constant yung voltage drop na yun na hindi naman nalalayo sa 2 volts or full load na nag-i-equal sa armature current times the brush resistance drop. Ay na-highlight ko where RB is brush contact resistance. Yung RB kinukonsider na brush contact resistance. Sumunod, yung nakaka-apekto sa voltahe ng generated voltage ng isang DC generator, yung tinatawag na armature reaction drop. Ito yung diniscuss ko sa inyo dati. No, meron pa nga itong video. Ito ay dahil sa demagnetizing component o yung pagkawala ng magnet. Yung mga dahilan ng yung mga component na nagiging dahilan para mawala yung magnet ng armature reaction. Tinatawag din itong armature reaction drop. At saka yung cumulative effect ng 1, 2, at saka 3. Pinagsama-samang epekto nitong tatlong ito. So sa note, armatures are made of windings having resistance. No, ang armature daw ay binubuo ng mga windings o mga ikid, no, na merong resistensya. So kapag merong maluwag na contact sa pagitan ng commutator at saka ng brush, magkakaroon ng pagtaas ng voltahe. Yun ang epekto mo. Let's go now to the external characteristic of generators. Yan, para sa separately excited generators, paano? Ano itsura ng external characteristic ng isang separately excited generators? Pag sinabi mong separately excited class, ito yung klase ng mga generator na independent yung magnetic field nila sa supply ng voltahe. So, independent siya kasi itong field windings niya, kumukuha ng supply yan sa outer source. Hindi katulad yung self-excited, ito, nakakonekta dito. So, kumukuha siya ng kuryente galing dito sa armature. Pero ito, separately excited to, independent ito dito. So, yan yung characteristic ng separately excited DC generator. So, simula rito sa B hanggang dito sa C, yan yung tinatawag na ohmic voltage drop ng isang separately excited generator. Simula dito sa C hanggang sa D, yan yung armature reaction niya, no? Ang pinakikita sa graph na ito kung paano bumababa. Kasi ang pinaka-ideal kasi, syempre, ito, nandito. Hindi. Dapat nandito. Kaya lang, bumababa ng bumababa. Kasi nga, dahil dito sa mga factors na to. Ohmic voltage drop, armature resistance drop, at saka itong ano, no? Itong mga lines na to, curves na to, pinakikita niyan yung internal characteristic. Tsaka yung external characteristic ito. Internal kasi nasa loob itong dalawa nito. So ito yung ideal. Kaya lang, hindi naman talagang nangyayari yan. Kasi bumabaksak talaga yung generated voltage niya. So ito yung characteristic ng separately excited generator. External characteristic of a separately excited generator yan. At saka yung factors causing the voltage drop. So ito sa x-axis, ito yung field current. No? Kung may graph ka, dito mo nilalagay yung scale ng field current. Tapos sa y-axis naman yung terminal voltage. Ito yung output. Yan yung nagsisilbing output niya. So kung i-graph mo yan, by means of these points, nakukuha yan by experiment. So ito yung parang yung pinaliwanag ko nung previous discussion natin na kapag bumilis yung takbo ng generator, tataas yung voltahe niya hanggang ma-reach niya yung saturation point niya. So pag na-reach niya yung saturation point niya, unti-unti na siyang bababa. magde-demagnetize siya. Ayan. Ayan, ito yung pinaka-ano niya, no? Yung point na nagpapantay sila nitong magnetizing at saka itong demagnetizing sa point na yan. Hanggang sa hindi na siya magge-generate ng voltage kahit bilisan mo pa ng bilisan kasi na-reach niya na yung saturation point niya. Yeah. So nakadepende rin siya sa ano, no? Nakadepende rin siya sa computation at yung klase ng design sa kanya. Kahit bilisan mo, siyempre, pag binilisan mo, tataas ng tataas yung voltahe. Kaya lang, pag na-reach niya na yung saturation point, magde-demagnetize siya. Na ibig sabihin kasi na magde-demagnetize. Kasi, ang armature, pumuputol ng magnetic flux galing sa field poles. E ngayon, pag na-reach niya na yung saturation point niya, magsisis o hihinto yung pagsusupply ng armature ng kuryente sa field o yung field poles. Kung ano siya, kung self-excited, separately pala itong pinag-uusapan natin. Separately excited, although sinasabi natin na tuloy-tuloy na yung energy o yung supply na tinatanggap niya from an external source, darating pa rin siya dun sa saturation point niya. Because the machine is designed only at a certain maximum voltage. Pag lumagpas ka pa dun, kahit bilisan mo pa, bilisan pa yung ikot niya. Kahit na tuloy-tuloy pa yung supply dun sa field, hindi na siya makakapag-generate ng voltage. Kasi na-reach niya na yung tinatawag natin na maximum rated voltage. Hindi na siya mag-susupply ulit. Yung sumunod ay separately excited generator itong pinakita ko, no? Tsaka yung graph niya. Susunod naman natin yung tinatawag natin na series generator. So, series generator yan, no? Yung no-load voltage niya ng ganitong klaseng generator ay magiging dahil sa residual magnetism or yung tinatawag natin na latak, magnet na latak. So, yung series generator, yung no-load voltage niya or yung no-load voltage ng ganitong klaseng generator dahil dun sa residual magnetism niya. Dahil walang kuryente dun sa series field at saka wala siyang excitation, no? Ano tong excitation na ito? Wala siyang katulad ditong separately excited generator na ini-excite yung field para makapag-produce ng magnetic flux. So wala siyang excitation. So yung generated voltage niya ay nakadepende sa load current. Kung ano yung kuryente ng load, yun din ang kuryente niya. Naka-series kasi siya eh. So yung series field, aasahan mo na susunod yan dun sa trend ng magnetization curve. Ito yung nasa kaliwa ay characteristic ng isang separately excited. Ito series generator kung pinag-uusapan natin. So sa series generator, meron siyang tinatawag na curve na ganito ang itsura. No? Ito yung load in amperes, yung load current niya. Ito yung terminal voltage niya. So yan yung external characteristic ng isang series generator para sa isang constant o hindi nagbabagong kuryente na lumalabas sa kanya sa pagitan ng terminal A and B ng series generator. So ganito itsura ng isang series generator. So tinawag ito short shunt kasi itong field poles naka-short lang siya, no? May click. Hindi siya nakasagad dito. Pero ito, nakasagad dito. Tingnan niyo itong series field. Hindi naman siya dito nakakonekta eh. Dito lang siya sa kabila. Nakakonekta pa ganyan. Pero ito, nakarekta dito. Ito, imbis na dito nakakabit, dito siya kinabit sa taas. Long shunt, tsaka short shunt. Compound generator siya. So ito yung characteristic niya. Ito yung yung load current niya Ito yung output voltage niya. Sabi ko nga, ang pinaka-ideal sana, yung nandito sa taas mismo. No? Para sa flat compounded, ito yun. Yung over-compounded, ito yung characteristic. Ito yung tinatawag natin na cumulative compound. Maabot siya hanggang dito. Simula rito hanggang dito, yan yung para sa flat compounded. Ito. Simula rito hanggang dito sa mga ito, under-compounded to. Simula rito hanggang dito. Or simula rito lang pa, tama, hanggang dito. Sakop to. Tapos simula rito hanggang dito para sa shunt generator to. So, ito yung tinatawag na differential compound, yung nakaganito. So, dito na tayo sa application. No? Application o separately excited generator. So, maganda siya para sa mga power installation. Katangian niya or yung taglay niya na may tendency siya na magdala ng humawak ng terminal voltage na constant kung ito ay may interpol. Kaya suitable siya powers para sa installation. So, doon tayo sa application no, ng separately excited generator. So, maganda siya para sa mga power installation. Kasi dahil yun sa katangian niya or yung taglay niya na may tendency siya na magdala ng humawak ng terminal voltage, na hawakan niya yung terminal voltage na constant kung ito ay may interpol at ang armature winding ay low resistance. No? Kaya suitable siya powers para sa installation. So, doon tayo sa application no, ng separately excited generator.
In this video, I'm going to share some shocking information about separately excited DC generator. So with this in mind, let's jump. Hey, this is Rudraj and you're watching Learning Vibes. This is another video on video lecture series on DC machine. You can see on display, this is the classification of DC generator. This classification we have studied in our previous video. In that video, we have seen this thing with animation in circuit diagram and its wiring diagram. And I have told you why that thing is important while we are understanding the working and numerical of DC generator. So if you want to learn that thing, the link of that video is provided in description box below and above here in card. So you can watch that thing later on. Now we'll quickly jump to the applications. So we are going to learn the application of separately excited DC machine. Basically, this separately excited DC machine has variety of applications. The first application of separately excited DC generator is in Ward-Leonard system. It is used there because of separately excited DC generator. It can produce output voltage in very wide range, and because of this wide range we can give this variety of voltage to DC motor, right? And because of this wide range of voltage availability we can vary the speed of motor in very wide range. So this is the reason why separately excited DC machine is used in Ward-Leonard system. Now let's see the second application. Basically, it is used in many laboratories where we need to understand open circuit characteristics, speed torque characteristics, and many other applications, many other things of DC machine. And to understand all these things, we need to perform various experiments like open circuit characteristics of DC machine, like speed regulation of DC motor, and many things. Right? So for this purpose, we require a DC generator who can operate in a wide range of voltage. So that is why this machine is used in this type of application. And one more thing for that conclusion. If you want to learn all these experiments like open circuit characteristics, speed regulation, I have prepared a separate video for that. Just go there, watch that video and learn those things. with experimental setups. Go back. Okay, so now we'll move towards the third application. Now in the next application, it can be used as a source of DC motor. This DC generator has a separate field excitation, and because of it, it can be operated in stable condition for wide range of induced EMF. And this is the reason why it is used to supply the DC motor. Now let's go for the next application. The response of this DC generator is very fast, and that is why it is used where quick responsiveness is required. Quickness and responsiveness is the most important thing. At that moment, this type of generator is used the most. In the next application, it is used for excitation of large alternators. Basically, the large alternator requires DC excitation to produce a constant magnetic field, and this generator is used to produce that DC supply, right, to excite that winding in large alternators. Come closer. If you want to learn the working of large alternator with animation, then the video for that is in the link below. Just go there and check out that video. Now again go back. So that is why this type of separately excited DC generator is used to excite a large generator. Now let's go for the next application. They are also used as auxiliary and emergency power supply for the loads. So now let's move ahead. Before moving ahead, there is a quick short question for you. And the question is this: why separately excited DC generator is used in supplying a DC motor? Write the answer of this question in comment section below. The same thing I have taught in this video. So just think, imagine, and write the answer in comment section below. And before writing the answer in comment section below, do not forget to hit the like button, because your one like helps a lot. That motivates a lot, right? So if you want to keep watching this type of video, do not forget to like this video. Now, let's see. This is all the application of separately excited DC generator. In next video, we will see application of shunt generator, and the link for that video I will provide it in description box below or above here in card, or you can watch that thing in end screen. If you want to learn anything more on DC machine, on any other topics of electrical engineering with animation, then write that topic in description box below, and I will make sure that I will make video using animations, so that it will be easier for you to understand all those complex fundamentals. So until we meet in our next video, till the time, bye bye.
Okay, yun yung mga application ng separately excited generator, no? Nakasummarize dun sa video. Last meeting, nag-play pa nga ako ng video kung saan ay discuss ko sa inyo yung iba't ibang klase ng application ng series generator. Tulad nga ng sinasabi dito, may kukunti lang siyang application bilang generator. Kung yung isa sa mga application niya o pinagagamitan sa kanya, yung ginamit sa Europe, dun sa tinatawag natin Curie system sa pagtatransmit ng power. Ang naka-invento nito ay itong si Curie, binase sa pangalan niya. So, itong si René Curie, na nabuhay sa pagitan ng 1860 hanggang 1938. Na isang Swiss pioneer sa electrical engineering. Nakilala siya sa kanyang mga gawa sa mga matataas na voltaheng direct current electricity na ginagamit pang transmission, at nakilala rin siya bilang professional sa buong daigdig, o tinagurian siyang hari ng direct current. Yung tinatawag na Curie system, power generation, gumagamit siya ng DC supply para sa pag-generate ng electricity. Ito yung picture. Yan yung 1882 Curie 6-pole dynamo. Mas compact daw yan kesa dun sa ginawa ni Edison. Yung maliit na 1,300 kilogram or 2,900 pounds na version na na-produce siya yung 22 kilowatt at 600 RPM. Pero yung mas malaki, yung 4,500 kilogram na 9,900 pounds, yun ang version na nagpo-produce ng 66 kilowatt at 350 revolution per minute. So balik na natin yung yung tawag doon, application. So ginamit yan sa Amerika bilang booster ng electric railway system. So ginagamit siya po. Hanggang ngayon naman ginagamit pa rin ng DC sa mga tren katulad sa LRT. DC yun. Anong patunay na DC yun? Kung titignan mo yung tape cable dun sa itaas at sa baba, yung kumikislap habang dumadaan siya. Katulad nung ginagamit din dun sa mga cable car sa mga mall. DC ginagamit nun. So number 4, Roman number 4, application of compound generators. Ang mga compound generators naman ginagamit sa kahit na anong uri ng generator. Ito ay ginagamit para ma-maintain yung constant voltage sa kabilang dulo ng transmission line sa pamamagitan ng paghahabol niya dun sa line drop. Ginagamit ito para ginagamit din ito para mag-supply ng ilaw, pang-ilaw, no? At saka mga mabibigat na mga load, power load na nangangailangan ng constant o hindi nagbabagong potential service katulad ng electric railway at yung iba pa mga motor drives na matatagpuan sa mga plantang pang-industrial. Ginagamit din siya sa mga steel industry na kung saan nangangailangan ng maraming amount ng direct current power na ginagamit sa mga motor driving rolling mills. Tayo ng sample ng DC electric air railway, no? So unang-una, sa mga application ng compound generator, ginagamit siya para mapanatili yung voltahe na hindi nagbabago sa kabilang dulo ng transmission line pamamagitan ng pagtapat dun sa line drop niya. Yung isang application ng compound generator.
This is take 2 of our quick demo of this compound forklift traction motor. Take 1 was unsuccessful due to a crappy camcorder battery. So some quick emergency engineering. We have adapted this battery here with some high quality cables here to power up the camcorder. So fingers crossed this will do the trick and I can actually film this thing. Okay, so what we have here is essentially a forklift traction motor. Came out of a Mitsubishi forklift. Let's try to get this here without a glare on it. There we go. And you can see the basic specifications there on it. In its forklift applications, it is designed to be powered from 72 to 80 volts DC. So I hope to be able to increase that a bit for the car. Okay, so just a quick explanation of the test that we're going to do. This is essentially a compound DC machine. So what that means is that it's got 2 sets of field terminals. The first set is high current stuff. It's this terminal here and the one down here, and this is designated S1 and S2. This is the series field, and up front here these 2 smaller terminals here, F1 and F2. These are the shunt field connections, and on the back here we have A1 armature, and let's take that crock clip off. There we have A2 in there. Okay, So those are our armature terminals. Now, essentially, what I want to try to demonstrate today here is the shaft speed against field strength. So what we have two power sources. The first one here is just a standard 12-volt car battery, and then I have three smaller 12-volt gel batteries here. They're hooked up in series to give us 36 volts total. Going to hook up one end of our shunt field here, and just leave the other end disconnected for the minute. So the first basic power up that we can do here is just to connect it as a normal series machine. So if I connect up the battery here, we'll see something happen. I'm trying to get that terminal to stay on, and we can see there that the shaft is spinning up happily. Now, if I apply a load to this shaft here, as we can see, I'm trying to be careful, you can see the more that I squeeze it, the slower it gets, but the slower it gets, the more torquey it becomes. And that's the characteristic of a series wound DC machine, that being that the torque is essentially inversely proportional to speed. So the slower it gets, the more torque it has. The faster it gets, the less torque it has. Okay. Now, the next thing that we're going to do here is I'm going to start back up again, and I'm going to apply 36 volts DC to the shunt field via our gel batteries here. Okay, I'm trying to do this single-handedly here now. So I'm going to connect the series power back up again, 12-volt car battery. Now we're spinning away. So now I want to observe the shaft speed as I connect the 36 volt DC shunt field. Now, as we can see here, the shaft speed has just dropped appreciably. Now the characteristics have changed. That is, when I apply a load to this motor, it tends to maintain its speed, because now it is behaving partly as a shunt machine. And a shunt machine, I'm squeezing the hell out of that now, and I can't stop it. And if we disconnect the shunt field component, our shaft speed increases again. So that is a simple demonstration of the difference in torque and speed characteristics when a motor is ran as a series machine or a shunt machine. In this case, I've got the best of both.
So sa video na yan, pinapakita yung application ng compound generators. Paano pinapakita yung doon? Kung i-analyze mo, pinipigilan niya yung torque speed, no? Pero yung compound generators, may characteristic kasi yan. May katangian niya na yung speed niya ay constant, hindi nagbabago. Hindi nagbabago yung speed ng motor or generator at the same time, pero motor usually sa mga railway, kahit na magdagdag ka pa na magdagdag ng load, yung pagpipigil niya dun sa torque, parang dinadagdagan niya ng load, pero yung speed hindi nagbabago, ganun pa rin.
It might be surprising to know that in electric trains, the power collected from the overhead lines ends up in the grounding cable of the track after flowing through the wheels. Three-phase power conversion, regenerative braking, and zigzag overhead lines. All these make electric train technology quite unique. Let's understand all the engineering secrets behind the electric train, starting from the simplest design possible. The simplest version of an electric train is shown here. Here, a single sliding wire collects electric power from the overhead lines. This power is fed to a single-phase induction motor. The induction motor's rotor is connected with the wheels. To complete the circuit, the induction motor's other terminal is grounded. This grounding connection is possible because the wire is first connected to the wheels through an axle brush. The wheel is always in contact with the track, and the track is grounded, as shown. You can see how the current from the OHL flows to the ground. It first passes through the induction motor, then the axle brushes, then the wheels, and finally to the track and ground. When the current passes through, the induction motor's rotor spins, along with the wheels. However, a spinning wheel will move forward, which means the next grounding circuit should be available at a very short distance from the previous one. Now, let's look at some axle brush details. The axle brushes are fitted to the rotating wheel, and the current is transferred to the wheels through these carbon brushes, which slip over the disc attached to the wheel axle. Again, this is the simplest version of an electric train. Now, let's improve this design and make our train more functional. The voltage used in the overhead line is 25 kilovolt, which is a huge voltage. Motors require much less voltage to run. For this reason, we need to feed it to a step-down transformer, which transforms the voltage to the desired level. The power supply from the overhead line initially passes through the transformer's primary, and here, the circuit is completed due to the grounding. Because of the transformer's action, the current will be induced in the secondary winding and reduced voltage power is fed to the motor. For high traction like the train, the motor should supply a high torque. Moreover, the torque curve should be uniform, even if the motor speed varies. Three-phase induction motors are the perfect choice to achieve high, uniform torque requirements. Stretching three-phase wire to power this motor is not a good idea, as it's highly uneconomical. That's why a rectifier and inverter is used to convert the single-phase supply to the three-phase supply. A rectifier converts the single-phase AC power into DC power, and then the inverter converts the DC power into three-phase AC power. Now this engine is ready to run over the track. We can increase the torque output further if we add a transmission system with some gear ratio between the motor shaft and the wheel axle. At this point, the engine we just made seems perfect. However, if we make a complete train by connecting several coaches to this engine, it becomes quite clear that the single motor engine we developed doesn't have sufficient power to pull all these coaches. So, let's add more motor wheel pairs to make the engine more powerful. An engine bogie is constructed with three-phase induction motors, obviously to drive 3 pairs of wheels. In an engine, generally 2 such engine bogies are used. In this complete engine, you can see how the transformer and rectifiers are positioned. So far in this video, we've shown how we transfer power to the train using a single hanging wire. However, this method is not practical. Sometimes it is not possible to keep the distance between the train and overhead line the same, which means for proper power collection, a height-varying mechanism should be used. Pantographs accomplish this task. A modern pantograph looks like this. You can see that based on the pressure of a pneumatic system, the pantograph can adjust its height. If you observe carefully, you can see that during this height adjustment, the current collector remains horizontal. The current collector has to be perfectly horizontal. Otherwise, power transmission will be in trouble. We hope from this animation you can understand why the current collector always remains horizontal. For more details of it, please watch our detailed video about the pantograph. Now, let's see the pantograph in action. If for some reason the pantograph loses its connection with the wire, the train will continue its free run for a few kilometers due to high momentum. Have you ever wondered why the overhead line stretches in a zigzag manner? This arrangement ensures that the pantograph's collector head doesn't touch the overhead wire at a constant point of contact. Due to this arrangement, the wear and tear is minimized. We can control the speed by changing the induction motor power supply's frequency. This is accomplished by the rectifier and an inverter. The driver sets the lever onto a different notch to change the frequency and hence the motor's speed accordingly. The most important aspect for the train, after acceleration, is stopping. How is this accomplished? Should we directly turn off the induction motors? If so, the train will keep on running over the tracks for several kilometers until it comes to a dead stop. Another idea is that we could apply electrical braking. In a normal induction motor, the rotor speed is lower than the speed of RMF. However, by lowering the supply frequency, we can reverse this condition. Interestingly, when RMF speed is lower than the rotor speed, the direction of induced current in the rotor bars reverses. This makes the induced torque on the rotor in the opposite direction. This is a perfect brake. A brake without metal-to-metal contact. During this phase, the motor runs a generating mode. However, this braking method can't stop the train dead in its tracks because regenerative braking doesn't work at low speed, which means it can slow the train down. But after that, you have to apply the pneumatic brakes to stop the train completely. This is a different kind of mechanical brake. Here, the spring force and compressed air forces are acting on the piston in the opposite directions. The interesting thing is that when the driver releases the air from the cylinder, the stretched spring pulls the piston towards the wheel and the brake gets applied. This brake system also provides security in the case of air leakage or broken compressor. The brake gets applied automatically as pressure releases. The pneumatic braking system is fitted under every coach for each wheel pair. Now, let's see how the power is supplied to each of the coaches. One way to supply the power supply for each coach's utilities is by self-generation. An alternator is mounted under the coach frame and driven by a cardan shaft, which is driven by a gearbox mounted on the axle. Output is rectified and charges a 110-volt DC battery, creating a continuous power supply to coaches. But this self-generating method is not efficient as it produces very fluctuating output power. So the most common way to supply power to the coaches is head-on generation. In this method, an extra winding is added up in the locomotive transformer, which supplies the power to all the coaches. Thank you for watching the video. See you next time.
Ay AC din siya eh. Sa mga modern, no? May application na ng AC. Pero kung sa DC, gagamit ka ng compound generator. No? Ginagamit siya sa mga heavy power tools, loads requiring constant potential service such as electric railway. So, ginagamit siya para mag-supply ng pailaw at saka nagbibigay din siya ng heavy power. Kaya niya rin ng heavy power loads na nangangailangan ng hindi nagbabagong potential sa serbisyo, katulad ng electric railway at iba't ibang motor drives na matatagpuan sa plantang pang-industrial. No? Ginagamit din siya sa mga industriya ng bakal kung saan nangangailangan ng malalaking amount ng direct current power na magagamit ng mga motor para mag-drive ng rolling mills.
This film will give you, as a student, an overview of the processes within a hot rolling mill. The film is made in collaboration with SSAB in Borlänge. Here, the steel material is processed plastically at very high temperatures. Rotating rolls reduce. The material is heated in the reheating furnace, rolled in the roughing mill, coil boxed, rolled in a finishing mill, cooled and coiled. Before the slab can be processed, it must be heated. The slab is continuously cast and has the dimensions required for the final product of a correct weight, width, and thickness. These furnaces heat the material to about 1200 degrees centigrade. Two walking beam furnaces feed the material through the oven. The heating is especially important as it affects the properties of the material. If the material is not sufficiently heated, incorrect material properties will arise. This is due to carbides and nitrates failing to dissolve. During the heating process and the transport to the roughing mill, the hot material reacts to the oxygen in the air, and a mill scale consisting of oxide is formed on the surface. If the oxide layer remains on the material during rolling, the layer risks being rolled into the steel material, adversely affecting the surface quality of the final product. The material must undergo a mill scale cleansing before rolling. In order to cleanse the surface, water is sprayed at high pressure, 160 bar. After the material has undergone a surface cleansing, it's sent to the roughing mill. Here, the material is rolled from its original thickness of 22 centimeters down to about 3 centimeters. This is a very significant reduction. At this roughing mill, a powerful 4-high rolling mill is used. That is, 2 backup rolls and 2 smaller working rolls. The backup rolls are often cast steel rolls. The working rolls must have very smooth surfaces and tolerate high temperatures and wear, as they are in direct contact with the material. This particular material is rolled with 5 passes, where 1 pass means that the material passes through the rolls once. The material is surface cleansed several times during the roughing mill process to remove any new traces of mill scale. In order to control the width of the material, vertical rolls are used. The material is now called transfer bars. After the roughing mill, the transfer bar is rolled up in a coil box. The coil box's primary purpose is to save space, but when inside the coil box, a temperature equalization also occurs. The temperature difference between the ends of the material is minimized as the transfer bar is coiled together. When the transfer bar is removed from the coil box, it has a temperature of about 1050 degrees centigrade. The ends of the transfer bar are cut off, and the bar undergoes further mill scale removal. After this, it's time for the next stage, the finishing mill. This mill consists of 6 stands in the shape of 4 high rolling mills. Here, the transfer bars, now called strips, are rolled into a thickness of between 16 and 1.8 millimeters. Between the rolls, we see an up looper, which measures and controls, amongst other things, the line speed and the strip tension. The swinging motion that can be observed is when the up looper is adjusting itself.